Hello, and thank you all for joining us for the Pando Days 24-25 project premieres and this event. My name is Eugene Shirley, President Pando Populous and co-host of the Pando Days event, which you've gathered for, along with my dear friend and collaborator, Matthew Manos. I'll be hosting all of these events. I'm hosting those that are happening today. Matthew and I will be trading off over the coming weeks. Pando Days is the program that makes it easy for young people to make something happen for the world and for their communities. We're excited to be with you because today we'll get to see what the Pando Days 24-25 project teams have been up to. Each team is given 15 minutes to present summaries of their projects, followed by 20 to 30 minutes of Q&A from a panel of experts. These premiere events are recorded, and in early 2025, the recordings, along with all project materials, will be posted on each team's dedicated webpage to be found on the pandopopulous.com website. Projects are then judged by a distinguished panel of specialists with honors and prizes and networking opportunities galore at the Pando Awards in April. That event is April 27. Please mark it on your calendars. So let's get started. Today we'll be hearing from Citrus College, led by Tommy Reyes, with a fascinating and potentially enormously useful project with this goal to develop a residential climate system designed to give you a constant internal temperature in your home of between 68 to 72 degrees. It will reduce your cost of heating and cooling to a minimum and take stress off the electrical grid. Sounds to me like a dream come true. And if it can actually happen, then of course there's a ton of potential. Tommy, you brought us an amazing project last year, and now you're back, promising to blow us away. So please do. The floor is yours.
All right, thank you, Eugene. So yeah, like you said, that's our goal. It's we set it really high. If we come close, great. If we make it little, even greater. So we did a pre-recording. I'll go ahead and share that pre-recording, and then the students are here for some Q&A as well.
Hello, everyone. My name is Professor Tommy Reyes at Citrus College, and this is our Adobe Wall System submission. And we're going to go ahead and introduce some of our members of this project, starting with Celine.
Hi everyone, my name is Celine Anna. I'm majoring in computer science here at Citrus College.
Hi, my name is Koi Goki. I am majoring in construction engineering and construction management.
Hi, my name is James McMahon. I'm majoring in civil engineering at Citrus College.
I'm Joshua Tobor, majoring in engineering, automotive technician, and machinist.
Hello everyone, so today we're going to learn about Adobe. It's a special kind of mud that people have used to build their houses for a very long time. We'll talk about three main things that make up Adobe. We have clay, sand, and straw. Let's get started. So for clay, think of clay like as a glue. It holds everything together, making the Adobe stick. Second, we have sand. Sand is like the muscle. It gives the Adobe strength. It keeps it from cracking when it dries. We have the straw. Straw is like the secret ingredient. It makes the Adobe flexible and helps it breathe so it doesn't crack in hot or cold weather. So what is R value? It's kind of like a superhero power for building materials. The higher R value, the better a material is at keeping heat where we want it. A high R value means it can block heat from coming in during the summer and keep it in during the winter. Now let's talk about Adobe and compressed earth blocks. These are great materials, but they don't have a super high R values. This means they don't block heat as well as some other materials. Um, so while they're great for many reasons, like being eco-friendly and strong, they might not be the best choice for keeping your home super warm or cold or cool. We use R value to first pick the best stuff. We can compare different materials like fiberglass, foam, or even natural materials to see which one is the best insulator. Second, we can save money. A higher R value means less energy is needed to heat or cool our homes. So we can save our money on our energy bills. Third, build smart. So we can use our value to choose the right materials for walls, roofs, windows, and floors to make our homes as energy efficient as possible. For the super adobe is a modern twist on an ancient building technique. It uses a special mix of mud and lime packed into plastic bags. So these bags are then stacked and held together with barbed wire. This method makes building very strong, especially against earthquakes. So, for example, we see that this house, that there was a house in 2017 in Mexico, survived an earthquake of a 7.1 magnitude, um, and they also let in plenty of light and air and can help keep homes cool in hot weather. So while Adobe is great for many reasons, it's important to note that it doesn't insulate as well as some other building materials. So this means it might not be the best choice for very cold or hot climates. For Hyper Adobe is a modern take on traditional Adobe construction that offers several advantages. So by incorporating lime into the Adobe mixture and compressing it into special fabric bags, this technique creates a strong and durable building material. One of the key benefits of Hyper Adobe is that it's affordable. So the use of these less expensive bags reduces the overall cost of construction. Also, Hyper Adobe structures are remarkably resilient. Why is that? So they can withstand extreme weather conditions, including floods, fires, hurricanes, snowstorms, and high winds. This makes Hyper Adobe a suitable choice for building in regions prone to natural disasters. And now I'm going to pass this thing to James.
So why experiment with Adobe mixture ratios? It's for cost effectiveness, strength, durability, longevity, and the health and the environment. Our first mixture ratio is going to be with sisal fibers. Here we have 50% sand, 50% soil, 30% sand, 10% lime, and water is needed. So more about sisal fiber. It's a natural fiber extracted from an agave Sicilian plant and can significantly improve the properties of adobe, a traditional building material made from clay and water. The benefits of sisal fiber reinforcement is the increased strength. The fibers bind clay particles together more tightly, making the adobe stronger and more resistant to cracking. Improved flexibility. The fibers add flexibility, enhancing the adobe's ability to withstand seismic activity and other stresses. Enhanced durability. The fiber's resistance to moisture and rot helps protect the adobe from deterioration, extending its lifespan. And the way it will be incorporated into the adobe is to cut the sisal fibers into short lengths, mix the fibers into adobe mixtures during kneading, and mold the mixture and allow it to dry slowly. By incorporating sisal fibers, builders can create more durable and resilient adobe structures. Next, we have volcanic ash mixture. Here we have 40% soil, 30% sand, 10% lime, and water is needed. More about this mixture. Volcanic ash is a fine-grained material produced by volcanic eruptions and be a valuable addition to adobe mixtures. When incorporated into adobe, volcanic ash can significantly enhance the material's properties. Some of the benefits is increased strength. Volcanic ash fills the voids between clay particles, creating a denser and stronger matrix. Improved water resistance. The fine particles of volcanic ash can help reduce water absorption, making the adobe more resistant to moisture damage. Enhanced thermal insulation. Volcanic ash can improve the thermal insulation properties of adobe, helping to keep buildings cooler in hot climates and warmer in cold climates. The way this will be incorporated into adobe is to mix volcanic ash with the clay and water to form a homogeneous mixture. The optimal ratio of volcanic ash to clay can vary depending on the specific properties of the ash and the desired characteristics of the adobe, and then is molded through the mixture into bricks or directly into the wall and allow it to dry slowly. Next, we have the salt fiber mixture ratio. Here we have the soil 50%, sand 30%, lime 10%, and water is needed. More about basalt mixture is it's a volcanic rock as well, can be crushed into a fine powder and added to adobe mixtures to enhance its properties. Some of these strengths are, like the others, increased strength, basalt hardness, and durability contribute to its increased compressive strength and resistance to wear and tear. Improved water resistance. Basalt can reduce water absorption, making the adobe more resistant to moisture damage and freeze thaw cycles. Enhanced thermal mass. Basalt can increase the thermal mass of adobe, helping to regulate indoor temperatures and reduce energy consumption. And The way this would be incorporated is to crush the basalt into a fine aggregate, mix the basalt aggregate with clay and water to form a homogeneous mixture. The optimal ratio of basalt to clay can vary depending on the desired properties as well. And now I will pass it to Josh.
Thank you, James. In addition to the homogeneous materials, we will be adding a plaster made out of natural lime. The ingredients to make this plaster will be 1 part coarse sand, 1 part lime, and 1.5 parts of sand plus clean water. We'll be adding 1/2 inch of thickness to the adobe wall. In addition to the plaster, we'll be integrating chicken wire to these homogeneous mixtures. Why add a high thermal conductor that will just increase thermal transmittance of materials in the wall, causing an increase in U factor, resulting in a higher rate of heat transfer. We're using this because it will allow this wall to be stronger. And all these mixtures will stick better and stay in place, making it less likely to fall off or weaken here in California during an earthquake. Chicken wire will spread out any stress, helping prevent cracks inside the plaster, especially during seasonal changes between hot and cold to hot. This will hopefully increase the lifespan of our walls. And by adding this, each layer will adhere to each other more cohesive and making the plaster a more smoother and more even surface. In order to dry these materials, we have to keep the wall between a 68 to 86 degree Fahrenheit environment. We must avoid extreme heat. Anything about 95 degrees Fahrenheit will cause rapid drying, leading to cracking. We must also be aware of our humidity levels. Too high of humid will cause a slow drying process, or too high of humidity will cause a rapid evaporation. But to help us control these variables, we will be using a tabletop oven that will allow us to control our temperatures that will not exceed above 95 degrees Fahrenheit. And our timer will allow our humidity levels to be variant between how long we keep these materials inside the oven. Up next will be Koi with our stress test for various Adobe recipes.
Thank you, Josh. For this project, we actually are going to try to conduct a couple engineering tests, and the stress test is one of them. We're going to test the block's unique actual compressive strength. We're basically going to flip the block to its side and put it under pressure and wait until it cracks, and then measure the PSI per square inch to see how much of each block can handle. So the goal is to basically create a block that can withstand earthquakes and our minor disruptions of Southern California. Another thing is the hydraulic binders that we could combine, like cement and lime, to strengthen and improve the compressive strength of these blocks. Like my teammate said, that we have volcanic ash, we have sisal fibers, we have basalt fibers. Those all help with the compression and strength with the block once they're dry. The impact test that we're going to be conducting, this will assess the durability and resilience of each block that we create for each recipe. The drop weight test, basically we're going to drop a certain amount of weight on each block until it cracks. And then we're going to do the pendulum impact test. This will allow us to see the impact of something running into it. For example, if the mass wall is near a street or a car hits it. This will see how much damage these bricks and blocks can actually handle before failure. So once we do the pendulum test, we're going to check the amount of energy absorbed, and then check how much of the block is basically cracked. We're going to measure the crack, what type of crack it is, if it's a shatter cracking, if it's just a straight line crack or a fracture, and then we'll go from there to see how much more it can handle before it fully fails. We would like to actually do an earthquake test, but we don't have the materials or programs to simulate that at the moment. So if we get access to that, that would be nice. But at the moment, we're trying to figure that out. But it's a test that needs to be done here in the state of California to make sure the mass wall stays in one piece and doesn't fail. The heat and cold test. Adobe's not very good at being cold. It actually absorbs heat. So we're going to measure how much heat it's going to take on a standard Adobe block, which is a 10 by 4 by 14 block. So we're going to plan on heating up one side and see how long it takes to reach the other side of the block by measuring the the heat in Fahrenheit with thermometers and thermal. Another test we would like to do is the miniature wall with the interior wall and see how long it takes for the heat to reach the gypsum board. And the cold test, basically what I would like to do is to get it to freezing temperatures and see how hot or how cold it could get before it cracks and fails. The heat test is another thing is that we're going to heat up the block until it cracks, and we're going to videotape as it heats. This is actually the Adobe wall system that we created. It's your standard 10 by 4 by 14 blocks, but buttress supports in the front that you can't see on this angle. The design, there is number 4 rebar inside the wall as well for building codes in the state of California for mass walls. There are other materials of standard rebar that can possibly be used. This is the side view. There's the buttress right there that actually helps support the mass wall. These have actually been used throughout the history of architecture from Europe to here. There's the interior wall as well. You'll see on the next slide. So here's the side view again, but with the Adobe brick and the rebar inside. You can see the metal stud framing, the gypsum board, the standard insulation. You can use fiberglass, you can use spray foam if you want. We're sticking with fiberglass because it's for cost effectiveness. The insulation barrier, the vapor barrier inside will help keep the moisture between the wall, interior wall, and the mass wall for moisture. And here's the stucco finish. The stucco finish will actually help waterproof and protect the actual Adobe blocks because Adobe is not waterproof and it's not water resistant because of the clay and sand. But with the new type of blocks that we're trying to create and what our recipes, we're hoping to create a water resistant block or possibly a stronger Adobe block to help building costs here in the state of California.
And that concludes our presentation.
Hey, Tommy and team, thank you. Thank you so much for that. There were all kinds of things that I found fascinating. I'm going to hold back on my comments, though, until we can bring in our experts. We have 20 to 30 minutes now for an informal back and forth discussion about the project, how to assess it, and where they think, and we all think, you all think it can go. Returning today as a pillar of the Pando community, Mark Spears and Richard Haskell, who only a couple years ago was sitting in the opposite chair. He was team lead of a Pando Days project then. Richard is professor of physics emeritus at Harvey Mudd College in Claremont, where he was teaching for almost 45 years after being trained and getting his PhD from Johns Hopkins. As I referenced earlier, he was also team lead for an extraordinary project from Harvey Mudd, Pomona College, and Cal Poly Pomona, with the aim of manufacturing a revolutionary solar panel in neighborhood factories across the county. It's an extraordinarily visionary project. And Mark Spears returning to the respondent's chair. Mark helped us conceive and launch Pando Days 5 or 6 years ago, key in founding the CSO, Chief Sustainability Officer Task Force for LA County, served as founding CSO of one of the Southland's flagship companies you may have heard of, Walt Disney Company. Mark is now in league with USC, advising young entrepreneurs. And I understand members of the Burrell Happold engineering firm are joining with us today. Burrell Happold, you'll all know, authored the LA County Sustainability Plan, and Pando Days is produced in partnership with them as one of our core sponsors, about which we're honored and delighted. Thank you, Burrell Happold, for your support. Ling Kai Sin, I believe you're from Burrell Happold. Is there anyone else whom I'm missing from Burrell Happold right now?
I think Kim
Hi.
was
Yeah,
up.
I'm Kim
Oh,
Pfeiffer.
Kim.
Yeah.
Oh, hi.
Hi. I'm
Hi.
a principal in the Los Angeles office of Bureau Happold.
Thank you so much for joining us. And Ling Kai, thank you so much for joining us. Are you also here in the Los Angeles office?
Yes, mechanical engineering in the LA office.
Okay, terrific. Well, I'm delighted that you both can be here. So let's do this. We have plenty of time for a Q&A. What we want to do is start off, we'll ask Dick Haskell to get us going. Then Mark, why don't you come in, and then Kim or Ling Kai, either one of you, or I mean, one after the other, however you want to do it, join in afterwards, and then we just have an open, free for all discussion after that. Okay, Dick, take us away.
Okay, thanks. Well, first I should say that I was really attracted to this project because it is potentially a really a shattering of tradition in terms of architecture and construction and materials and so forth. And you all know that. But I'd like to begin with just a clarifying question. I noticed in the presentation, there was an R value of R2 associated with one of the materials. And I'm just wondering, did you measure, or how much did R values play in your analysis and sort of strategic research that you've been doing? And were you able to measure R values from some of these materials?
That's a great question, Dick. We were not able to measure anything yet. We are in the process of designing forms for the bricks that we're going to create and test. We decided that it was too much of a task to do it all in one semester, and we just decided let's just get the research done. In terms of the R value, we knew that Adobe didn't have the greatest R value, but the value of Adobe was that it was able to absorb heat and not really transfer it into spaces. And that's why we kept the existing wall structures that have the fiberglass insulation, because that has a great R value. But if we can block the sun from ever reaching that wall, it potentially increased the R value in itself.
Okay. Mark, you want to jump in? I've got more, but we should probably trade off here.
Sure. Well, thank you. And thank you all. And I think it's always amazing to sort of look at a back to the future concept here, where we're talking about very traditional, very ancient construction methods that are now actually being, brought towards the future. So congratulations to you all on that. I think part of the question I have maybe lifts off Dick's questions about existing building regulations and how we think about that relative to the work you're doing. Do you envision this fitting within existing regulations, or do you envision that there has to necessarily be adaptation that would be required, say, at the state or federal level?
Yeah, that's a great question, Mark. We discussed this, and if this were to actually be approved by a city, it definitely have to be approved by the state and the building code in itself. I'm not aware of what that process looks like to get them to look at it. As of right now, we do have one of our members that they're not here today, but their brother is a structural engineer, and they're taking a solid look at what we've been designing, and they're ready to do the calcs as soon as we can get our stress tests done. And I think once we present a preponderance of evidence saying that this could potentially work, or not potentially, actually work, then I think we need to bend the state's ear and say, hey, we need to look towards this. This could be something huge where it could save a lot of money for everyone in the long run.
Yeah.
And reduce the amount of energy needed to run our grid.
Dick?
Great. Yes. Okay. So here's a question that occurred to me at a number of points during the presentation. I'm not sure this idea was actually articulated, but I just have a feeling that it's underlying your thinking as you approach this project. And that is, and Tommy, you just mentioned that Adobe actually, these materials tend to absorb heat. and not just sort of, prevent it from passing through, but absorb heat. And so I'm just wondering, it may be that the use of Adobe historically has enabled the sun to warm, it would be absorbed during the day, so it get hot. And then during night, when you actually want some to keep the temperature up, it would then be flowing through. And I thought that idea, is appealing. I'm not sure how easy it would be to really take advantage of it, but it just seems very sensible.
Yeah, we took a look at an architect out of New Mexico. His name was it escapes me right now. But he did something similar. He didn't use Adobe. He packed used tires with dirt to create enough thermal mass between the interior of his structures and the exterior of his structures. And he was able to achieve between 68 and 72 degrees on the inside. And this is in Taos, New Mexico, where it snows, where it's over 100+ degrees on a regular basis. And he's all year round, 68 to 72 degrees. And so we know it works. We just need to be able to work in California and make it look aesthetically pleasing. Because that's what we do in California.
Kim or Linkai, do either one of you want to come in at this point?
Yeah, to be honest, my question was going to be right along the same vein. Is that it's the thermal mass of the Adobe that's the most important. So what I would say is I think in your research, instead of, I mean, you should include the R value for each of the materials you're looking at, but more importantly, include the thermal mass of the materials. There's a number, it's a property of Adobe that you could probably do some research and find that number. It's a certain BTU per cubic foot per degree Fahrenheit. It's a metric that you can assign to a material. I think it would be nice to see that for the different types of materials that you're looking at as it compares to traditional building materials. I think also, Richard, you made a point about being able to have a thermal exchange between the wall and the inside of the space. When you have that insulated wall on the inside of the Adobe, it actually breaks that down, right? So you're not actually getting the beneficial radiated heat from the wall into the space at nighttime because it's being blocked by that insulation. So just something to think about if the purpose of the material is to really create a nice thermal condition on the inside, you might want to consider comparing with and without that extra layer of insulation on the inside.
Thank you. That's a great idea. Thank you.
And also, I think one point out on Kim's statement is that the task you can see is you can just measure to the temperature at the inside and outside and see how that peak is delayed by using this this wall. So you will see like the outside maybe peak around noon, then inside peak at like 4 p.m. or 5, and that will quantify the performance of that material. So that can be interesting too. Yeah.
Thank you. Yeah, we definitely want to test for that. Going into this, we thought we can design and come up with some tests before the end of the semester. Like, ooh, this is way too much to handle. And so we decided let's just get the research done and prove that this is possible. And then we started on some forms. In fact, Josh created some forms for scale model. And so we're going to start testing probably next semester.
I think what I also would have appreciated is maybe at the beginning of the presentation, a bit of an executive summary, right? So someone like me, I don't know anything about your project. This is literally the first time I'm hearing it. And you guys jumped right into the sort of research, but I would have liked to see an executive summary of what's your hypothesis, what are the conclusions you've made so far, and you said you were trying to see if it was possible to use this material. Like, what exactly are you trying to achieve in the building by using this material? Is it less energy use? Is it stronger? Is it cheaper? Is it easier to build? Why do you think that this is a material that people should be using?
We are trying to control all the forms of heat transfer, such as conduction, convection, and radiation that can be found in all homes. So through this, we hope to stop air drafts by compact or tight fittings to reduce that convection side of heat transfer. Uh, um, that way the convection inside the home stays inside, and through the chicken wire, maybe reduce that conduction between the outside and the inside and regulate the thermal differences. And with our fibers that we chose, we hope to remove such as spray foam that can be chemically bad for the people inside, especially when it's first put on to the wall. It is chemically unstable. It can cause fires. So if we can avoid bad chemicals and go with the natural substance, then we can have a healthy environment for our families.
That's
I
great.
think
Those
what
are,
I think. Oh, go ahead, Kim. Sorry.
no, I was gonna say those are two really good reasons, right? Regulating temperature and creating health in for the people, and regulating temperature. To take it one step farther, the reason we want to do that is so we use less energy in heating and cooling a home, right? And with less energy, we have less carbon into the atmosphere. So sort of just like following that train of thought of like, why are we doing this? And making sure that that's part of your story that you're telling.
So another reason is also cost effectiveness of the materials. Since Adobe is made from clay and sand, it's all around us. It's a natural material on Earth. Dirt comes cheap to nothing, basically. And it's been used throughout the world. So when we decided the volcanic ash, the basalt fibers, the sisal fibers are being used in Adobe in Mexico constantly. And then the basalt and stuff has been used in the Middle East in their Adobe buildings. And some of those buildings have been standing for centuries. We have our missions here in California that are built from Adobe. Adobe has unique characteristics for the heat. It doesn't just absorb heat, it releases heat throughout the day. So even at night, even if it's 10 degrees, I've been in New Mexico where they use Adobe all the time up in Taos where Mr. Reyes was talking about. I've seen these airships, I've helped build them and stuff. So I have experience with Adobe. And yes, what you mentioned about the fiberglass insulation in the interior wall, it doesn't really disrupt it. Actually, it'll transfer the thermal heat to the insulation, which will eventually hit the wall, the gypsum board wall, and it will warm the house. So there's pros and cons, and what the basis of it was if we could create a brick that's fire resistant, water resistant for here in Southern California at a cheaper cost of building than concrete, then right now we're in a housing crisis. We're in an energy crisis, no matter where we go in the United States. We live in the Southwest region. Adobe's all around us. It's cheap material to build. Natives been using it for centuries. It's easy repair. It's easy to be replaced. The problem is the water resistance and the strength and durability that it has. But I've been in negative 16 up in Angel Fire, New Mexico. Lived in an Adobe house with interior walls. And it was still, we got it up to like 80 degrees in the winter. So there is a possibility. The thing is that like Mr. Reyes says, it's all about cosmetic looks. Adobe, you can't really make fancy designs off. It's cheap material to build a house for cost effectiveness, for energy. So there's a lot of applications you could do. The thing is like, how strong can we get this material for people don't break their banks, for energy cost, and that's what we're trying to find out. That's why we chose the different fibers from different regions around the world, because they're actually being used. Now, what happens when we start crossing these different fibers, like Kevlar carbon fiber? Well, some of these fibers are fire resistant. The lime will help make the adobe more water resistant, along with the volcanic ash and the sisal fibers. So there's things that haven't been done in research yet. The hyper adobe and the super adobe, they instantly went to lime. And yeah, adobe's cheap, but those companies that created these, it's the bags. They sell the bags for these, and those cost arm and a leg, so that's where they make their money. But creating a simple 10 by 4 by 14 block out of natural materials and mixing it by hand, everything's usually mixed by hand. A shovel in a bucket, shovel, or on the ground on a piece of board. You mix it and stuff like that. So it's all labor cost. You're not really using much on gas, on other materials. So with this project, we were hoping to actually reduce the cost of building and help energy bills. So that's what we were talking about and thinking about as the students. And I know there's a lot, we didn't get to the test. There's a lot of tests that we would like to do. And when we find out the information, more it comes, the more we could actually proceed and produce research results. And yeah. Is there any other questions that you guys?
Well, just to underline, I think what Kim is getting at here is I don't think anybody's questioning the genius of the idea. I think it's the point here is the business case needs to be established up front. What problems are you solving for? Because if you're going to go out and try to get somebody to invest in this,
no,
ultimately you're going to be testing the technology, right? And let's just assume it works. It's what issues are you solving? And let's say California housing crisis, environmental crisis, insurance crisis. This thing cuts across all of those, right?
all of them, yes.
So I think if you setting that story up front and then showing that this is a solution, to that issue, which is cost effective, which is durable, which is scalable, which uses, natural materials. I think that's sort of the storytelling that you can wrap around this to make it a really compelling solution.
Like I said, when we get the test results and we start making them and designing them, and we actually get to do the engineering test, stress test, and all that stuff, and we'll be able to see a lot better. The University of New Mexico has done a lot of research on Adobe, but they did traditional Adobe and not regular Adobe. So Adobe, the R value of 2, someone asked about it. That is actually the regular R value of a mass wall of Adobe for the 10 by the regular block of Adobe is what the University of New Mexico tested for that. And so even in New Mexico and other states that use Adobe, they have an interior or exterior wall. So sometimes the Adobe's inside, the wall's inside the house, but they have insulation on the outside. So they have another wall system connected to the Adobe wall. So in that, they actually put different insulation in it. Some of them use the wheat insulation, some of them used regular insulation, fiberglass. I've seen people use the ripped jeans and stuff. They shove that in there. So it's experimenting which insulation is the best. So I know she had the question about the insulation interior wall and stuff, but even traditional building, they use an insulator on the outside or in the inside of the wall for the interior wall, or they build an exterior wall on the outside and the Adobe walls on the inside. So, but
So
I understand.
A question maybe extending that is your thoughts, if you've gotten this far, on what the target market. Is this new construction? Is it rehab construction? Is it?
It will be my target idea was not just for the energy effectiveness, but also like cost effectiveness. If someone wants to build a house here in the state of California, for example,
It costs a lot. You know, you'd be dumping up $800,000 and up more on materials, and it's just another option of building and possibility lowering the cost for like California. You know, when they build the housing systems for low income, it might be a idea where, you know, the cost effectiveness of building these housing communities for low income might, okay, let's use Adobe instead because, you know, it's going to save us some money for the state. I wasn't just thinking, I was kind of thinking across the board. Like you said, you know, it crosses a lot of businesses, insurances, advice, and like so on. Like I was thinking about that whole thing. And like when you guys talked to Mr. Reyes about how would you present this to the state? Yeah, it's something that the state, the county, the cities have to look at to see if it's viable. Because insurance companies are probably freak out about it. They're just like, oh, it's a giant wall, you know. So it's something that you don't really see in the state of California anymore. Even though it was here, the remaining remnants are our missions that we have here, and those have been standing forever. And we've all, I don't know if you guys been to them, but like in the middle of summer, they're cool inside. So the Adobe not just, it help cool your house too. So in the middle of summer, it'll still be cool inside. So you don't have to kick your air conditioner on.
And we designed it in such a way to where it could be for existing structures as well. And that's why you see the traditional wall. And so our intent was to be able to come up with this system, not just for new construction, but for existing as well. So no one's going to have to go down and tear down their whole house to be able to have this application up against their wall. And so that not only is new construction part of our target market, but existing structures as well.
Tommy, it's I mean, it seems fascinating to me. Of course, I'm a non-specialist, but but still as a layperson, certainly does, and I've enjoyed all the comments and questions. The remaining one, from my perspective, is where does this go? And you've indicated a little bit, you know, along those lines and the kind of testing that you want to do, next steps and all that. But if you could just talk to us about that a little bit more.
Sure, absolutely. Yeah, after our testing and we have, you know, the data that we want to collect and the proof that this is a viable option, we want to go to our structural engineer that is on board to doing the calculations, to actually coming up with a viable wall system that we can present to the city of Glendora. I'm going to talk to them and see if they can take a look at this data that we've collected, the wall system that we designed, and see if it's possible that we can move this up to a state level and eventually get our building codes to adopt this type of wall system.
Okay.
So-
Well,
So I have
with you.
yeah.
Go ahead, Lynn.
So I actually have a question based on that. Are you then proposing, you designing a new product that you would patent or try to license based on the kind of brick that one of the models of the bricks that you're designing and testing?
Right, because we're taking recipes from different parts of the world and we're just like, hey, let's try this one against this one and mix it together and let's see what happens. And once we're able to do that, then yeah, we can potentially patent this. That's what we're looking at. And maybe even start a construction company that can specialize in creating these wall systems for existing structures. And basically get that going before we actually start on new construction. Because of course there's going to be opposition, skepticism, but you know, we got the math and the data to prove it.
Mm-hmm. No, that's great. So my suggestion actually is building a little bit on Kim's. I mean, I think it's fascinating and it's really important. But I would urge you to figure out to place the context in your presentation. so we know why, we know the problem that you're trying to solve, that we know that you're solving it within an innovative solution, and what are the benefits of this solution? It's availability, it's affordability, it's sustainability. Because you've all talked about all of this in the presentation. I mean, you've talked about it in the discussion afterwards. And I think we need those elements in the beginning of the presentations, because like you have the middle right here. And you need the beginning, and then you need the end of what's going to be happening next. And, I know that you've said you're testing, but like, what kind of a timetable? What are you thinking of? When are you going to get to this? And then, as you said, the objective of presenting it to kind of the city and ultimately the state.
Yeah, no, we definitely need to add that to all our presentation slides. And I'm glad you pointed that out. This was we bit off more than we can chew when we started researching this, for sure. But yeah, you're right. And in order to come up with a marketable product, we definitely need to put those things in there. So
right. And you also mentioned to me when we were talking before about hoping to do it, a scale model, and, kind of like that's a little bit in your timeline when you don't have to have everything done now. But what I think what we want to hear is what you're doing next, or then, the steps that you're going to, the timetable for your future work, because it's it's fascinating, and I think a really good project.
Thank you. Thank you. Yeah, Josh was working on the molds. We got some silicone and we 3D printed some scale bricks that we used to make the mold. And so Josh had already made the mold. Coy is going to be making the life size molds for these. And so that's essentially our next step, is to figure out how to create these bricks so we can test, and then figure out how to scale up from there. Once we get all the data that we need. Because scaling up is going to be a mission in itself to tackle, in addition to getting it approved by the state as a viable form of construction. So thank you.
It will be fascinating for us all to watch as this develops. Thank you so much. It's time to wrap up, but this has been a wonderful presentation, wonderful Q&A session with you all. Mark, Dick, Ling Kai, Kim, thank you all for your comments, questions, and insights, and the Citrus College team. Our next premier event will be on December 16 from 1 to 2, and it will be with CSU Fullerton. Some of you may remember they brought us an amazing food security app last year, developed by a team of computer science and electrical engineers, student-based. Last season, it promised to help people be less food insecure by increasing the efficiencies that the app would produce. And I'm very eager to see where that project is going, and track the traction that they have made and figure out what they're doing this year. Thank you all again for joining. Enjoy your weekend.
Thanks,
you,
everyone. Great
Thank you.
presentation.
Yeah.
Thanks
Thank
for the
you.
feedback. Thank you so much.
Thank you for joining,
Have a
Kim,
good one.
Ling Kai.